Okay, here we go. Our lovely implicit differentiation. So this one here was asking us to find the second derivative. Okay. So got our crazy looking function here. All right, so we're going to take the derivative using implicit, then we'll solve for dy dx, and then we'll take the second derivative. All righty. So x squared plus y squared equals 8. So our derivative of x squared powered down, so that will be 2x plus derivative of y squared, again, power down, 2y times dy dx equals derivative of a constant, flat line is 0. All right, now we're getting dy dx by itself, so I minus the 2x. So now I have 2y times my dy dx equals a negative 2x. And now I divide by the 2y. So our dy dx is negative x over y. And now we got to do a derivative of that, which is going to be a quotient rule, which is going to be ugly, but we can do it. I believe in us. All right. So I'm just going to go ahead and rewrite it here. All right. So when you take the derivative of a derivative with respect to x, like you end up with dx of whatever you're taking the derivative of, which in this case is already a dy dx. So you end up with two d's. So that's why the squared is on the d. And then on the bottom, you end up with dx dx. So that's why this one is dx squared. It really should be written with parentheses around it. And then as you take more derivatives, you'd put threes, fours, whatever number there. So that's just how the differential notation works. So taking our second derivative here, low d high minus high d low, square the denominator, away we go. So ends with go, starts with low. So our low is y times d high. High is negative x. The derivative of that would be negative 1. Then minus from our formula, high, negative x, d low. So now it's just y, derivative of y is 1 times dy dx, which you could just write dy dx. Over square the denominator, and away we go. All right. So technically, I did the thing. Realistically, when they say find the second derivative, they actually want it in terms of x and y, not also in terms of dy dx. Luckily, we happen to have this handy dandy formula for dy dx. So we're just going to put it in there and do a little bit cleaning up as we go. So our second derivative of y with respect to x, that is a negative y. Then the minus and negative here will become plus x times negative x over y, all over y squared. WebWork should take this. Emphasis on the should. If it did not, then I would think of my all divided by y squared as times 1 over y squared and split it between the two. So that'd be negative y times 1 over y squared. And then now it'll be minus x squared over y times 1 over y squared. So normally I'm very hesitant to actually cancel things, but when we're doing the second derivative here, all we would use it for would be to plug in points, x and y values, and then find out information about the second derivative, which can actually tell us about the graph. We'll see that after the next test. So this would be negative 1 over y minus x squared over y cubed. That is our ridiculous second derivative cleaned up and without dy dx in it anymore. Now, like I said, that blue formula there should be sufficient. This is just if web work is being web work. But still, not too bad. You just got to remember your rules. Keep remembering every time it's a y, tack on a times dy dx, because we're just following our chain rule. All right. So first I was just like, y to the fourth minus 5. Yeah, that's not bad. And then I rewound and went, ew. We can do it. It's okay, but ew. All right. So we have crazy ridiculous equation. We want to find dy dx. All right. I see you, crazy problem. So y times the sine of xy equals y to the fourth minus 5. All right. So y times sine xy is a product. And then inside that, we're going to have we'll have a chain rule that then will spawn another product. So this is where, as silly as it sounds, going back and having a lot of practice doing the product rule so you can do it without having to label all the parts and write out the formula every time is beneficial. I know it sounds silly to say go do more homework, but you're trying to get this down to a muscle memory level of knowing. All right, so y times the sine of xy. All right, so first we'll take the derivative of y. So that will be dy dx. And we'll keep the second one, the sine of xy. Plus, now we keep the y, and we're going to do that crazy derivative. So derivative of sine ugly is cosine ugly. Times, now we need the derivative of ugly. Since ugly is x times y, this produces another product rule. So I derivative my x, which is 1, keep the second, plus I keep the x, and derivative of y is 1 times dy dx. So all of that is the left side. Equals. Now over here on the right side, we have a y to the fourth power rule, 4y cubed, times, inside is a y, so dy dx, minus 5, derivative of 5 is 0. Okay. So a little part of me is tempted to just be like, nope, done, but no. If WebWork asked us this monstrosity, WebWork would want us to actually solve for dy dx. All right, before I can even start thinking about solving, I have here parentheses and a sum in there. So I need to take this whole thing and distribute through to each of those pieces. All right, so I'm going to take this front guy. I prefer seeing dy dx at the end. It's just like my visual. Otherwise, it like starts to look like I'm trying to apply to the derivative to more than I really am. So I'm just letting y'all know why I'm doing this. There's no particular reason. And you know what? Now this is another example of, let's do the y prime now. Plus, this one will have the y cosine xy times y. So we will have y squared cosine xy. And then plus xy cosine xy times dy dx. And then on the right, we just keep that ugly mess exactly the way it is. Ugh. Sorry, forgot I was going to the y prime notation. Okay, so now everything that has a y prime goes on one side. Everything that does not goes on the other. We factor and divide by the crap. So that's why earlier in this, the steps, like this is the steps after you do the calculus step. Now it's all algebra, just rearranging so we can get y prime by itself. All right, so this y squared cosine xy is our only term that does not have a y prime. So I'm going to minus it to the other side. And then this y cubed y prime, I'm also going to minus it, so it's on the side with the y primes. And I'll just put it here. And again, like nothing is ever like terms. It's a, oh my God, shock when it happens. So don't expect anything to ever combine. If you're like, how do I combine this? Odds are you don't. All right. So in the interest of writing what we have now, so I have sine xy times y prime. That's gone. Plus xy cosine xy times y prime minus 4y cubed times y prime equals negative y squared cosine xy. Everybody on the left has a y prime, so we are going to factor it out. So that is now sine of xy plus xy cosine of xy minus 4y cubed still equals the negative y squared cosine xy. So then our derivative, our dy dx, is going to be what's on the right divided by that huge thing. So rather than write divide by and then another line, I'm just going to skip to dy dx equals negative y squared cosine of xy over sine xy plus xy cosine xy minus 4y cubed. Now it can be really tempting seeing the cosine xy and the cosine xy to want to cancel. No, do not do it. The only way we can cancel in a fraction is if it's the common thing times everything else. So there's got to be like parentheses around all the rest. Here, I ain't got parentheses, I ain't got multiplication, I got a plus and a minus. Can't do that cancellation. Now, I know y'all know better. I'm just saying. So there is a horridly disgusting implicit formula for the derivative. This is also a very vague look into why differential equations is its own crazy course. Because differential equations, it's like you start with the answer and have to try to work your way back to what the function was. All right. And that's all of our missing stuff for 3.8.